Hello everyone. In this video, I'm going to go over some examples and applications of natural logs in regressions. We're going to start out with the dataset hprice2. This dataset shows housing data for many different communities in the Boston area. We have three variables of interest. Price is the median housing price in each of these communities. NOx is the nitrogen oxide parts per 100 million. This is basically a measure of how polluted the air is. And finally, rooms, the average number of rooms in houses in that area. This is going to tell us roughly how big the houses are. We're going to go over to Excel and run two regressions. We are going to regress the price on the log of NOx and rooms, and then we're going to regress the log of price on the log of NOx and rooms. The first thing that we're going to have to do is calculate those logs. I'm going to add a new column in for our log of price. To calculate this, I'm going to use a formula equals ln of this cell right here. Remember that in Excel, ln is the log function. Now I'm going to fill this formula all the way down. We're also going to need the log of NOx. I'm going to calculate the same way, ln, and then click on this cell right here. Fill that all the way down. I've now created all the variables that I need. We're ready to run the regressions. We're going to go into the Data Analysis Toolpack as usual. Select Regression. For our first regression, we are going to use just the price, not the log, as our left-hand side y variable. For our explanatory variables on the right-hand side of our regression, we are going to be using rooms and the log of NOx. So I'm going to select that whole block of variables. Remember to check off labels and then click OK. Let's take a look at these results. We're going to look at the coefficients column here. Remember that our dependent variable here is just price, not the log of price. So price is going to be in levels. And here, rooms is also in levels, not logged. So the interpretation for this coefficient right here is going to be for every increase of one room, the price of houses is going to go up by $8,162. This is the same interpretation that we've had in our basic regressions up to this point. Now, when we go to the log of NOx, this is where our interpretation changes. We have price on the left-hand side, but we have the log of NOx on the right-hand side, so we have a level log interpretation. What this means is that when the level of pollution goes up by 1%, then the house price will change by the coefficient divided by 100. So if I take the coefficient and divide by 100, I get about $109. Remember that the effect is still in dollars because price is still in dollars, not in logs. So again, a 1% increase in NOx will decrease the house prices by $109. Note that I'm saying a 1% change in NOx, not a 1% change in the log of NOx. Let's go back and run our second regression. We're going to go back to the regression window, and we are going to change our y range to our second column here, the log of price, as opposed to just the price. We're going to keep our explanatory variables the same. Let's take a look at what we have. You can see how the numbers in the coefficient column have changed drastically. They're much smaller now. That's because we have logs as opposed to levels on our dependent variable. Remember that rooms is still in levels, not logs, but price is now in logs, so we have a log level interpretation. What this means is that we're going from a change in one room over to a percent change in price. Now to calculate how much that's going to be, remember we are going to have to take our coefficient and multiply it by 100 this time because we're going from levels into logs, or absolute changes into percent changes. So this tells us that if the average number of rooms goes up by 1, then the prices will go up by about 30%. Now, if we look at our Knox coefficient, since prices are now in logs, we have logs on both sides. This is a log-log model. So we have a percentage change on both sides. What this means is that a 1% change in Knox, the level of pollution, is going to decrease house prices by about 0.71%. Again, this is a percent-to-percent interpretation. Estimating percentage changes is certainly a very useful application of logs, but there's actually one more application of logs that we can do, and that's estimating non-linear functions. I'm going to use the Cobb-Douglas production function to illustrate how this works. Remember that the Cobb-Douglas production function is of the form k to the a times L to the b, where k is the amount of capital, L is the amount of labor. Now I'm adding a third parameter to this, which I'm going to call c. C is just a multiplier on top of the whole production function that you can think of as productivity. And all these put together, c times k to the a times L to the b, is going to give us our output q. Now normally we would not be able to use a regression to estimate this because this is not linear in terms. It wouldn't make any sense to use a linear regression to estimate this multiplicative function. But logs give us a way around this. Let's demonstrate how this works. We're going to start out with our production function q equals c k to the a L to the b. We're going to apply logs to this by just taking the log of both sides. So we're going to get log of q equals log of c k to the a L to the b. This is where our log rules come in. Remember that when we have a bunch of things multiplied inside of a log, we can separate those out as follows. We take log of c plus log of k to the a plus log of L to the b. We'll use our other log rule, and remember that when we have an exponent inside of a log, we can take that out. So we're going to get log of c plus a log of k plus b log of L. Now, while we certainly could not use a regression to estimate our original production function, the equation down here looks a lot more like something we can use a regression to estimate. We've got two explanatory variables, log of k and log of L. A, b, and log of c, those are our parameters that we're going to try to estimate. And our dependent variable is log of q. So if we were to go into our data, take the log of q, the log of k, the log of L, run the regression, we're going to get estimates. So we're going to run a regression. And what we'll get is log of q hat equals log of c hat a hat times log of k plus b hat times log of L. Again, these three things here are going to be what shows up in our regression table. Log of c hat is going to be our intercept, and then a hat and b hat are going to be down there alongside log of k and log of L. But once we've done this, we are not quite done. We need to put this back into the original production function, because this is not the production function down here, this is our regression. We're now going to need to undo the logs to get back to our original Cobb-Douglas function. Remember, to undo a log, we're simply going to take the exponential of both sides. So we're going to take e to the left-hand side equals e to the right-hand side. I'm now going to go in reverse with everything we did before. We still have log of c hat there, but now I'm going to tuck that a hat back inside the log. So we'll have k to the a hat power plus log of L to the b hat power. We're going to use exponential rules to note that we have e to the log of c hat times e to the log of k to the a hat times e to the log of L to the B hat, all these multiplied. Now the e's and the logs are going to cancel, so we're going to get times k to the a hat times L to the b hat. The only thing we're left with is this slightly messy expression here, e to the log of c hat. Remember that log of c hat is our intercept term from our regression, so this is just a number. So to get our estimate of productivity, c, we're going to define a new estimate, c hat, that's just equal to e to the log of c hat. So you're going to take your intercept term, exponentiate it, and that's going to be our c hat. So we're going to get c hat times k to the a hat times L to the b hat. Remember that a hat and b hat, those came straight from our regression. And then we're going to define our q hat as follows. This shows that we can take a nonlinear function like the Cobb-Douglas, use logs to slightly transform it just enough that we can run a regression to estimate the parameters. The final application of logs that I want to talk about is elasticity. Elasticity is one of the reasons why log-log models are so popular. Remember that the definition of elasticity is the percent change in quantity divided by the percent change in price, or income, or other things. The point is that we have a percent change and a percent change. This is perfect for the log-log model. To estimate elasticity, all we need to do is take the log of both sides and run the regression. Before we do that, I want to talk about a few caveats. First of all, the demand functions that we've estimated previously, we've assumed that they were linear, meaning that we assumed a constant slope, but a constant slope implies a changing elasticity. The log-log model, on the other hand, assumes that the elasticity is constant, and therefore the slope has to be changing. It's impossible to have both at once. What I'm not doing is suggesting that log-log is always better for estimating a demand function, simply that both versions make assumptions. In reality, it might be that neither of these assumptions are reasonable, but just be aware that we always have to make assumptions of some kind when we are doing economic modeling. The act of making assumptions is not good or bad. What it is necessary for a tractable analysis, something that we can actually use. But it's important to think about whether or not your assumptions are reasonable for the situation that you're trying to model. We are going to go over to the demand dataset and estimate some elasticities. First, we will create logged versions of all the variables, and then we will estimate a model fully in logs. Log of q on the left-hand side and log of px, py, and m on the right. First, I'll make some headings here for log of qx, log of px, log of py, and log of m. I'll use the ln function again for my log of q, and I'm going to run the formula all the way to the right to get all three of the explanatory variables, and then we'll run it all the way down to get all of our data. Go back to regression. I will now select as the dependent variable log of q, and for the explanatory variables, the logs of our other three variables. Make sure labels is still checked and click OK. Let's take a look at our estimates. First of all, we've got negative 0.76 here for log of px. This tells us that a percent change in price will decrease the quantity demanded by 0.76%. This tells us that our demand is price inelastic, since this is in absolute value less than 1. For our cross-price elasticity, we can see that a percent change in the price of y will increase the quantity demanded of good x by 0.34%. This is positive, so this tells us we have substitutes. And finally, a 1% change in income will increase the quantity demanded by 1.13%. This is a positive number, and that tells us that we have a normal good. So these are our three elasticities right here, or at least estimates of them.